Hello class, Mr. Cordova here, bringing you section 8-1, areas of parallelograms and triangles. So let's get this one going here with our lesson objectives, which are to use formulas to find the area of a parallelogram and to use formulas to find the area of a triangle. We're going to start right off the bat here with Theorem 8-1. Theorem 8-1, which states the area of a rectangle is the product of its base and height. You're probably familiar with this one because you probably learned this back in 3rd or 4th grade or somewhere along those lines. So the area is here. Area equals the base times the height. So we have those right there, and we use this for any type of rectangle, and this will also work for squares, since a square is a type of a rectangle. Now, since a rectangle is a type of parallelogram, let's take a look at what the formula for a parallelogram looks like. So I'm going to leave the two definitions close by so we can see something. The area of a parallelogram, Theorem 8-2, is the product of a base and the corresponding height. The wording is a little bit different. The formula looks identical. Is area equals the base times the height. So we have those. But the deal here is that notice it does say a base and the corresponding height. Well, why is that different? Well, in a parallelogram, depending on what base I use as reference, the height that I use for the calculation is also different. So take a look here. I have base B here, and I have my height H in this label here as my height. So the reason we have this, if you notice my base, we go to this vertex, and from this vertex we draw our height such that when it hits my base it forms a 90-degree angle. Back when we did triangles, we talked about what the altitude was, and that's exactly what the altitude is. You go to the opposite end, or the opposite vertex rather, and you draw a line so that it hits the opposite side in here at a 90-degree angle. So this right here is my height. Now say for instance I could use another height, another base. For instance, I could say for instance I'm going to call this base. Okay, so that means I cannot use this height anymore. I need to find another height so I can actually go ahead and use this formula. To do this, I would then have to extend my base a little bit here, like so, like that. And then from this vertex right here, right, I would actually have to draw a line which becomes my altitude. So this intersection here is a 90-degree angle, and this will be my height, and then I can use the equation with this number here as my base and this number here as my height, and I would actually get the area of my parallelogram. We'll actually take a look at the use of that concept in a problem later on in this lesson. In the meantime, let's take a look at some other problems here. Actually, in this case, some concepts. So we have the base of a parallelogram, or a base of a parallelogram is any of its sides. Okay, well, you can actually use any of its sides. The corresponding height, actually in this case, the corresponding altitude is a segment perpendicular to the line containing the base drawn from the side opposite the base. Now, the height is the length of an altitude. Take a look over here, which is what I tried to go over a little bit earlier. You have here on the left a parallelogram and a parallelogram on the right hand side. So I can actually use this base right here and find this height right here, and if I multiply those two, I get the area of this parallelogram. I could also then use this side as a base, but then I have to find my altitude. In that case, I have to extend my base outside the parallelogram and then connect it from the opposite vertex right here, from right here to the base at a 90-degree angle. This now becomes the altitude that I need, and I can go ahead and calculate the area of the parallelogram that way. So it all depends what do you use for your base as reference. So let's take a look at some examples. So we have example 1, A number 1. So here we have example A number 1, in which we have a parallelogram, and we have some values already given to us. So we have the base of this parallelogram is 5. We happen to know this side right here, and we happen to have the altitude right here, or the height. The height is right here, so we have that information that we need. So for the area in here, we have the area equals the base times height. So this is going to be 5 times height, which is 4, and this will give us 20. But it's not just 20. Our units are in inches, and area is always in squared units. So if our units were inches, the inches come here and is going to be squared inches. So the area of this one is 20 square inches. All right. Moving to number 2, we have this length over here, and I want to point out that one of the misperceptions that I see a lot, specifically with parallelograms, not much with rectangles, because we don't have to do much of these auxiliary lines that you see here for rectangles, but in parallelograms we do. A lot of people actually see a parallelogram like this and they go, oh, the area is the 2 times 4.6, and there's my answer, boom, I'm done. But that's not the case. In this particular case, we have our base is 2 centimeters, right? Our altitude happens to be 3.5 centimeters. So this is the value that we use, the 3.5, okay? So our area equals still base times height. So we substitute our base is going to be our 2 here. Our height is a 3.5. And this is going to be 7. And it's 7, what units? Is centimeters, but we're dealing with area, so it's going to be centimeters squared. And that is the area of this particular parallelogram. All right. Now let's move on to some examples for you to try. Actually, there's just one for now. So let's take a look. As usual, as soon as I finish reading it, you pause the video and you give it a shot and see what you get. Good luck. Find the area of a parallelogram with base 12 meters and height of 9 meters. All right, let's take a look at what you got. So we know that the area of a parallelogram, it tells me that it's a parallelogram, so we know it is area equals base. I'm not going to use parentheses, I'm just going to do base times height. So we have our base is going to be 12 here times 9, and when we have that 12 times 9, we have that's going to be 108 meters squared, and that is our answer right there. Okay, so that's that for this problem. Let's move on with the rest of the lesson. And in here, yes, I know how much everybody loves graphing, but It's part of the concept. So it goes like this. Finding area in the coordinate plane. Find the area of parallelogram PQRS with vertices P1, 2, Q 6, 2, R 8, 5, and S 3, 5. So we need to find the area of this parallelogram. So how in the world do we do this? So, well, the first thing is we need to plot those numbers in. So we go to, in this case, 1, 2. So we have here, and that is going to be point P. Then we go to Q, which is 6, 2. 6 right here, 2 is right over here. So that point is going to be our point Q. Right, and then we go to point R. Point R is at 8, 5. So we go to 8 right here, and 5 is right over here. Then our last one is S, and S is located at 3, 5. So we have 3, 5 right here. And then I'm going to go ahead and connect those dots right here. So we have a line right there, a line right there, and I'll need to finish labeling those in a second. So we have that. So that this point right here, what was it, 8, 5. So this is R, and this is S. Alright, so we know that the area of a parallelogram is area equals base times height. So we need to know what the base is. Well, I'm going to use P as my base, right? So how long is this base? I'm looking here at the scaling. The scaling is 1 to 1. So each of these squares is 1 unit. So all I have to do is count my units. So I have 1, 2, 3, 4, 5. So that means, and I'm going to use a little labeling here. So it's going to be PQ, the length of PQ, right, times height, So we know that PQ ended up being 5. We need to know now what H is. H, so I need to draw the altitude, right? The altitude to the base. I could draw the altitude from point S, or I could draw the altitude from point R. It does not matter, but so I don't have to draw many lines. Instead of drawing 2, I can draw just 1 by drawing my altitude right here. So we're gonna go over here and draw it from point S to the base. So it's gonna be looking like this, something like that, and that is our height. Okay, now in this case we can just take a look. If we know it's 3 units, right? So H is 3 units. In some cases you might not be able to use your eyes to find out what the measurements are. You might usually have to use the distance formula, but in this particular case we got lucky enough that it lines up perfectly. So we know that the height happens to be 3. So we have 3 right here. Maybe draw a better 3. So then we just substitute. For PQ we have 5, and for the height we have 3, and that 3 looks terrible. 3, that one looks worse, times 3. Alright, and then this is 5 times 3 is 15. And again, we are not told what this Cartesian plane here is measured in, but area is still units, so we're going to say units, or actually we're going to say square units. Square units. Okay, and that's the area of this one right here. So we just plot the points in, draw our altitude where it applies, and then we find the length of the height, find the length of our base, and then we multiply the two, we get our area. Let's take a look at an example for you to do. I'm going to put it now on the screen, and this one also requires some graphing, so I'm going to leave it right there so you can read it. And it reads, find the area of parallelogram EFGH with vertices located at -4, 3, 0, 3, 1, -2, and H is -3, -2. So let's take a look. So have that one, take a look at this one, and give it a whirl. Alright. Yeah, I almost did this one for you, but not so lucky for you. Let's take a look at how we actually would do this one. So we still have to plot the numbers in. So we go in here, we need to find where E is. E is located at -4, 3. -4 is right here, 3 is over here. So we have, that's our point E. Then we go to point F. Point F is located at 0, 3. So we are here, and that is point F. Then we need G, which is at 1, -2, 1, -2 down here. I will need that menu. 1, -2 right there. Alright, and then that's point G. H is located at -3, -2. So we go -3, -2 over here. And there we have those points. I will go ahead and connect those points. And connect those. There. And there. And there we have our parallelogram. Actually, I left this one without labeling it. -3, -2 was point H. Right there. So at this point in time, we need to find out what, again, area of a parallelogram is base times height, and I'm used to putting parentheses, but base times height. So we know right now we could use the base as HG, right? So we know that B is the length of HG, and HG, if we take a look, our units are in ones as well, so 1 to 1. So this is going to be 1, 2, 3, and 4. So we know that HG is 4 units. Now we need to know what H is. To find what H is, well, we need to extend. In this particular case, we could extend, and I'm going just to do it on the left hand side because it's easier to see, but you could actually extend it from the vertex at F to the base right here. The reason I don't do it is because, well, maybe you can see it since it's going to be in a different color. So I'm going to take it from point F to the base. So I'm going to draw my altitude, so it's going to be right along the y-axis, like so. That's my height, and if I take a look at how long that is, the height happens to be 5 units. You see it's 5 units right here, 3 above the x-axis, 2 below it, so it's 5 units. So my height is 5 units. So when I take my area, the area is going to be 4 times 5, which equals 20, and is 20 what? It is 20 square units. Square units, because, well, since the units were not specified, we come up with square units, and we cover our tails with the requirements for area. And that is for example, this was example 2. So let's keep going here. Example 3. Now example 3, I'm just going to move this over here. Alright, it says Find a missing dimension. Now we could actually use the area to find a dimension. As a matter of fact, you can use area equals base times height, right? Let me redraw that A for area. We have 3 variables, right? So if they give me 2, I can calculate the third, right? Right now we've been calculating A because we've been given the base and the height. But in some cases, they might give us the area and one or the other, like the base, and we need to calculate the height. They might give us the area and the height, and we need to calculate the base, so on and so forth. But once in a formula like this, if they give us 2 variables, we can calculate the third. But let's take a look at how this problem actually works out. Problem 3, it actually states, find the missing dimension for parallelogram ABCD. Find CF to the nearest 10th. Find CF to the nearest 10th. So CF is over here. And you're wondering, okay, let's see, can I use a Pythagorean theorem over here? Well, I know that this is 10, and if this ABCD is a parallelogram, if this is 10, so is this. But I don't know what DF is, and there is nothing here that I can use to find what that is, so I really don't know how I can actually do that, right? So let's take a look at how we can find it using area. So let's take a look and first calculate the area. We can calculate the area of the parallelogram right off the bat because we know the base here and we know the altitude or the height in reference to that base, right? Because we know what DE is. So we have the area is going to be 10, which is my base, times my height, which is 12, and I get 120, and is 120, the units are in inches, so it's 120 square inches, right? That's fantastic. We got the area, but we haven't answered the question as to what's the length of CF. However, if you actually take a look at the parallelogram and I say, well, I could use the area because if I can use DA now as my base, that means that my altitude is CF. You see right here that CF in reference to DA, or AD rather, in reference to AD, CF is my height, right? My altitude. It actually comes from this vertex on the parallelogram down to my base, and the intersection here is 90 degrees, which makes it an altitude. So I can use that. So let's actually take a look. I'm going to say that the area, since I already know what the area is, we calculated it earlier, we can say that 120 equals, right, my base. But I'm going to be using AD as my base in this case, which is 13, times my height, which in this case, in reference to AD, my height is CF, which is what I need, CF. And now we can find out what CF is. So we divide both sides here by 13. We get CF equals 120 divided by 13, which gives me 9.2, and the units are in inches. But it's not inches square, remember, where CF is just a segment. It's a linear unit, so it's just plain old inches. So that is my answer here for CF. Okay, now let's take a look at part B of this problem, which is very similar. Let's see if you can figure this one out. So as soon as I read it, give it a shot and see if you get the same answer as I do. So it goes like this. A parallelogram has sides 15 centimeters and 18 centimeters. The height corresponds to a 15 centimeter base is 9 centimeters. Find the height corresponding to an 18 centimeter base. Good luck. Okay, so this one is telling me that the height for a parallelogram corresponding to 15 centimeters, the height is 9 centimeters. So I'm going to calculate the area, and again, the area equals base times height. So now that I have that, I'm going to substitute those values in, and I'm going to get that this is going to be equals 15 times 9, and 15 times 9 is 135 centimeters, and we're dealing with area, right? Centimeter and centimeter is going to be centimeters squared right there, right? Now that we have that, we want to know what the height would be corresponding to an 18 centimeter base. So let's find that out by taking the area that we just found, and we're going to be using the formula of area and say 135 equals, right? The new base is 18, so it's going to be 18 times that height that we're trying to find out. We divide both sides here by 18, and we get height equals 135 divided by 18, and that is going to be equals to 7.5, and that is going to be centimeters done. That is this particular problem. All right, let's continue here. Moving on now to triangles. We actually touched a little bit of triangles when we were dealing with triangles, but officially we're doing area of triangles here. So it goes like this. Theorem 8-3. Area of a triangle. The area of a triangle is half the product of the base and the corresponding height. And here's the word again, corresponding height. Why that is? Because again, depending on the base that you use for reference, the height will be also different. So in this particular case, the area, or not particular case, but in any case for a triangle, is going to be 1/2 the base times height. Okay? The area of a triangle is 1/2 the base times the height. Again, just like we did with parallelograms and rectangles, if you are given two of those variables, you can calculate the third. So keep that in mind. All right. So we have a base of a triangle. A base of a triangle is any of its sides. The corresponding height is the length of the altitude to the line containing the base. Basically the same concept. So if here, back to the drawing here, we have our base over here. Our height will be this one right here, right? So depending on what I do for a base, if I pick this base right here, right, in this particular case, this right here hits this one, or I can actually just extend it and see where it would actually land at a 90-degree angle. So that doesn't look like a 90-degree angle. I cannot assume that it is, but say it is, or we can just draw a line from here. So land over here until it hits here at a 90-degree angle, and that will be our altitude. But that's it will actually give you the same exact area. Anyways, so here goes our first example. Our first example goes like this. Find the area of the shaded triangle here at the right. So let's take a look. Again, we have our base here, and we have the height is given to us right here, and the height is my altitude. Here's my base right here. So I take this vertex that is right across the base, and I draw a line from this vertex here, and I would extend the base so they both meet, and when they meet, they should meet at a 90-degree angle, which is what happens here. And that measurement in this case is 6.4. So we're going to go ahead and do this. So it's going to be area, and the area of a triangle is 1/2 the base times height. So this is going to be 1/2 times the base, which is 10, times 6.4, and that's going to give me 32 square feet. Square feet because our units are in feet and area is always in square units, and that's the area of this triangle. All right, let's take a look at an example for you to do. All right, find the area of the triangle here on the right. Have fun. All right, let's take a look at this one. In this particular case, we have a 90-degree angle here, which makes this triangle a right triangle. One thing about the altitude of a right triangle, it happens to be that the altitude of a right triangle is always one of its sides. I have, if I take this base right here, if I use 12 as the base, my height will actually be this side right here, because it's the altitude. So from this vertex to the base, it's already a 90-degree angle. So this will be my height right here. Now if I take a look at the triangle using the 5 as my base, if I take the altitude to it, it will be from this vertex over here all the way down to a 90-degree angle, which already is. So I could use the 12 as my height or my altitude. So let's take a look at this. I'm going to be using the 12 as my base. So I'm going to say area equals half the base times height. So we substitute, we have 1/2 times the base, which is, I'm getting ahead of myself here, which is 12 times height, which is 5. All right, so we go ahead and multiply all of those together, and we get that this is going to be 30. But it's not just 30, it's 30 squared centimeters. And that is this one. Alright? Hopefully you got the same as I did. Now let's continue here on to an application here in the real world, which involves weather, and actually we can apply this in Florida because it actually deals with hurricane force winds. So let's take a look. It says, structural design. When designing a building, you must be sure that the building can withstand hurricane force winds, which have a velocity of 73 miles per hour or more. The formula F equals 0.004 times A times V squared gives the force F in pounds exerted by a wind blowing against a flat surface. A is the area of the surface in square feet, and V is the wind velocity in miles per hour. How much force is exerted by a 73 mile per hour wind blowing directly against the side of the building shown here? Alright, the first thing that we realize is that this figure, well, is composed of two figures, right? We have the roof, happens to be a triangle. The actual bottom portion of the building here is a rectangle. But how do we actually find the area of the full thing? Well, if we take the area of one and the area of the other, we add them together, we get the area of the whole thing. So let's do exactly just that. So we need to calculate the area of the triangle. So the area of a triangle the area of a triangle is 1/2 the base times height. In this particular case, we're going to go ahead and substitute here, and we have 1/2 times the base. The base, well, the base, they share a side, right? Since a rectangle is a parallelogram, if this is 20, so is this. So we know that this length over here is 20. So the base here is 20, so it's going to be 1/2 20 times 6. And that's going to give me 60, and it's going to be 60 square feet. Alright, that's the area of that one. Then we need the area of the rectangle. The area of the rectangle, the area of a rectangle is base times height. So that in this particular case, it's going to be our base is also 20, so it's 20. And our height is this 12 right here, 12. And we multiply those two, we get 240 feet squared, or square feet. And then we have that. So then we say the area of the side, which is what this figure is showing, the area of a side is going to be our 60 plus our 240, which gives us 300 square feet. But that is just the area. We haven't even answered the question just yet, so let's see what we need to do here. Now we need to plug this 300 into this formula right here. So we have force, and the formula we're going to be using is the one they gave us, 0.0044 times area times velocity squared. So we substitute those, and we get 0.004 times the area we found, which is 300, and then we multiply that by 73, but it's 73 squared, so 73 squared goes there, and we multiply all those, we get a number that looks like this, 6,394.8, and the force is going to be measured in pounds, so this is going to be in pounds. Alright, let's take a look at next example. Alright, now it says, suppose the bases of the rectangle and triangle in the building above are doubled to 40 feet, but the height of each figure remains the same. How is the force of the wind against the side of the building affected? So give this one a whirl, see if you get the same answer and if you can figure it out. Good luck. Alright, we actually have to do some of the calculations exactly that we did earlier. So we're going to do the area of the triangle. So I'm going to put area of a triangle. I'm trying to area of a triangle right there. We know that's going to be 1/2 the base times height. We happen to know that this is 1/2 times 40 now, right? Times 6. We get 120 square feet, right? We compare that to the earlier value, 60 and 120. Okay, we're trying to see something, if there is probably a pattern. Let's find out. Now the area of a rectangle, is going to be our base times height, and we're going to say the base is still, actually in this case, is now 40 times 6, actually times 12, not 6, times 12, because the height is 12 here, times 12, and we get 480 square feet. 480. Now we have those there, and if you take a look, the areas of these two happen to be double, right? So let's find out something here. So when we multiply these, this is double, that's double, right? So the area, the total area, I'm going to show you total area. Total area is going to be 120. And 120, I'm just going to put the units at the end, plus 480, right, is going to be 600. And this is 600 square feet. Now, notice that this 600 is exactly double that. So if I rewrite this as 2 times 300, that means how is the force affected? Well, this 2 means that whatever I use to multiply into the function, right, into the equation, force, right, is 0.004 area, actually the area, yeah, area times velocity squared. So I can actually just say it's going to be times 2 times 300 times the velocity squared, so it's going to be 73 squared. I can take that 2 and pull it in front, so it goes like this. 2 times 0.004 times my 300 times the 73 squared. And now notice I can say that the difference between the two, or how is it affected? Well, it's affected because the force doubles. The force, and we're not talking about the Jedi Force or Star Wars Force. The force doubles. And if you still have issues with that, you can still go ahead and calculate the area, the force, and the force actually comes out to be 12,786.6 pounds, rather, right? Pounds. So if you compare the two, still, if you take this number, you divide it by 2, you get the 6,394.8, which coincides with the fact that it's been doubled. So that's what happens if you actually go ahead and double the base on the actual figure. The area, first of all, does double, and it does affect the force in this example. All right, so this is the end of the lesson right here. Hopefully this was helpful to you. If you have questions, feel free to send me an email, or you can contact me on Teams. I'll talk to you guys next time, and please stay safe. Have a good one.